Hi, this is Jeff from the Ozark Mountains in Missouri, USA. Thought we'd do a quick update today on the state of the software for our CNC 64 project. I've spent quite a lot of time over the last few weeks working on the buffer system. There are two buffers, the output buffer and the code buffer. The output buffer is accessed both by the code generation system and the pulse output system, so it needed to make sure that when the interrupt-driven pulse generation system was running, it wasn't messing up anything that the code generation system was doing. Finally got that worked out, and it works quite well, and it's pretty fast. The code buffer holds our equivalent of G code, which I'm calling Commodore codes, or C equals code. That was backwards. The code buffer holds our equivalent of G code, but it's actually a pre-parsed code that a C# program goes through and spits out the right data for us to type in. Eventually we'll have that more of an automatic process. Also coming up, we're going to have some more Commodore 64 repairs. I just got in this bad boy, which unfortunately is not mine, but it belongs to somebody else who asked me to take a look at it, so we'll be doing a video on that soon. So let's take a look at this software and see what's going on. I thought we'd start by taking a look at some of the major ideas and then kind of intermix some of the code both on the PC and Commodore 64 side to give you guys kind of the view from above, or the big picture about what we're trying to accomplish. So we'll have a G-code parser that is PC based, or I guess you could run it on Linux with Mono. It's written in C#, and right now it takes a simple point-to-point input, which are in steps, not any sort of distance unit. And here I say it outputs 9 to 11 bytes that describe a line segment. We'll look at the code and go into that in a little more detail later. And for lack of a better name, I'm calling this the Commodore code for now. The Commodore symbol here. If you have any better ideas of what to call this, just let me know. And this is based on the Bresenham line algorithm. There's a link in the description to a good PDF on this, and I'll go over that a little more later. Right now, let's look at the state of code the C# program is in, and I'll give you an idea of what it does. Okay, here we have Visual Studio open. This is, I think, the Community Edition 2013, which is the free version. So when I get this up on GitHub eventually, you'll be able to play with it for nothing. This is a pretty generic form. Steps per unit right now is 1. Eventually that'll do scaling from if you're entering stuff in inches or centimeters. That's what that's for. Mod is how many steps it breaks up the line segment into, and then of course we have our 0.1 and 0.2. And you can see here that we're going from 00 to 512, 128. And if we, let's go ahead and run this. Oop, it's off screen. Here we go. So if I just go with what it's defaulted to right now and click go, this might not make a lot of sense right now until you read more of the paper on the Bresenham line algorithm, but index 0 right here is the complete move. It tells you it covers from 512 to 128. This is in decimal numbers, which I should have been more clear to put up on here, but I didn't. And these following 3 are breaking that down into maximum of 255 steps, which is what the mod here was for. So the first one goes from 00 to 255.64. dx and dy are part of what we calculate
in the Bresenham algorithm, the step X and step Y directions are just telling us which direction, positive or negative, that the stepper motors are rotating. And the fraction is sort of like a fractional step of the following axis, which in this case is the y-axis. And then our next one, we go from 255.64 to 510.128. You can see it's just a duplicate of the line above. And finally, we pick up the last few steps. And these are all in hex, which I should have denoted a little better. But anyhow, that's the output it gives. I'll probably add a couple more columns later, and I'll show you that and my ideas in just a few minutes. So right now I'm copying this by hand into the C64 program. And if we look at the code behind this now, so it's entering the points here. And it goes through and calculates all those things we saw. We'll look at the Bresenham paper shortly, and this will make more sense. But basically, the Bresenham algorithm was written, I think, in 1965 by a fellow from IBM for outputting to plotters, or maybe it was a fellow from HP. Anyhow, it was for outputting plotters, and the generic or to the screen is another use case for it, where you're concerned about the exact coordinates that you're plotting to. I'm not concerned about the exact coordinates. I'm just concerned if we need to take a step on either the X or Y axis. So it makes things a lot simpler. But you have to know which axis is leading and which axis is following. So here we're saying that if the line dx, the delta x of the line, is greater than delta y, we're going to run this section of the code. Otherwise, this is where delta y is greater than delta x. And then we're basically running the same code, but we're iterating over the y-axis since it's changing faster than the x-axis. If they're changing at the same rate, you have like a 45-degree line, it doesn't really matter what you do. Here is the Bresenham paper that I mentioned, and the link to this is in the description below. This is kind of the best practical explanation I found of it, and I'm going to skip ahead down to page 16. This is kind of a generic or pseudocode description of the final algorithm. So it's doing something similar to our C# code, where it's calculating the delta x and delta y and setting the directions based on which is greater, and it's running a separate part of the algorithm for if delta x is greater or if delta y is greater. Now, on an old computer system like the Commodore 64, doing floating point operations is very expensive in terms of time because there's no dedicated hardware to do that. So the advantage of something like the Bresenham algorithm is it does all integer math, which is a lot faster. This picture is a description of plotting a line to a screen and how it has to break it up into individual pixels that are kind of stepped along, and you can think of this as being similar to a stepper motor stepping to approximate a continuous line. So the basic idea is that we're going to find out which axis has the greater change in it, and we're going to iterate over that axis and figure out what the other axis should be. So here, if we're iterating over the x-axis, and then we're going to determine what the y value should be for each step along the x-axis, and then we're going to set the pixel or step the stepper motor as needed. And if we go along here, and I would encourage you to download and read this paper, it's a fairly easy read, we can see that all the math that's shown, except for this initial division up here, which is only done once to calculate the fractional increment, And actually we can get rid of that as well with the multiply, and since it's 2 times, we can just do a bit shift there. So we're using this Bresenham algorithm to output the numbers that we need for our algorithm on the Commodore 64 that generates the output pulses. On the Commodore 64, we're also using a very simplified version of the Bresenham line algorithm to iterate over that data and generate the step pulses. Over on the Commodore 64 side, one section of code we have is an output byte generator, and it reads the table of the Commodore code we just saw, and it fills a 256 byte circular output buffer. And then the pulse engine, which is the part that's run in the non-maskable interrupt, reads from that buffer, and the buffer is refilled as the pulse engine is consuming it. Let's take a quick look at that output buffer code and see how that works. Here is our code opened up in CBM Program Studio. This is a great development environment for Commodore computers. I will put a link in the description below. It's a free download. If you like it and use it a lot, you can make a donation to the author, which I would highly encourage. So here is our circular output buffer. It's 256 bytes long, which is a convenient size because as we're incrementing the pointer into the buffer, it's automatically going to wrap around after we hit, when we're on 255 and we'll increment it. That's 256, which will wrap back around to 0, so we get that automatic wrapping effect without any additional code. Oops. We have a quick routine to initialize the buffer. It sets the head and tail pointers to the same thing. And if you can picture, you've got 256 bytes of memory, and you have a pointer or an index that points to the head, which is the next place you're going to write, and you have one that points to the tail, which is the next place you need to read. As you write, you'll write to where the head pointer points, and then you'll increment it. And when you read, you're going to read from where the tail pointer points, and then you'll increment that. When they are both the same value, that means that the buffer is empty. This is a quick test. It's part of the code below that just tells us if the buffer's full or not, and you'll notice here I say it may not be needed eventually. I don't think it is any longer. I think I got rid of the need to test for this separately anywhere in the code. But I'll leave it in there for now in case I need to use it later. In an outbuff write, this is all there is to it, and these numbers here give the value of the number of cycles that line is going to take. I didn't account, for the branching and everything, so this is kind of, I think, the worst case scenario, about 33 cycles, which is the same for the outbuffer read. I think I might be able to trim this down a little more. I don't think I'm going to need to return or set the X to return it. I might be able to do that a different way, so might be able to save another 4 or 5 cycles there. So the process of writing to the buffer first checks to see that if there's room, and if there is, it'll write and automatically increment the pointer. If there's not, it's going to return the X register as 0, and the Z flag will also be 0. And in my code, I'm only really using the Z flag. So that's why we might not need to actually set the X. Here our output read is very similar, of course. It takes the same number of cycles. And in a similar way, it outputs the X, or is 0 if the read failed. In other words, there was nothing in the buffer. X is 1 if it's a success. I don't think we'll need X again. I think we can just look at the 0 flag, but we'll take a look at that later and see. The reason this works is that when writing to it, the writing operation is the only thing that will change the outbuffer head pointer, and the reading operation is the only thing that is going to change the tail pointer. So they're not trying to write to the same location in memory over each other so it won't get confused. And I had this done differently. Originally it used about 3 times as much code and was much slower, and I had a flags byte and everything was just a mess. And I was chatting on the 6502.org forum about this and got some really good ideas, and found out that indeed having that flags byte was really not required, and it made the code a lot simpler without it, and it works great. The pulse engine is what runs under the non-maskable interrupt. It is running at a 1 kilohertz rate, courtesy of timer B on CIA2, which generates the non-maskable interrupt. It looks to see if there's available data in the output buffer, and if there is, it sends the next byte to port B of the user port. So let's have a quick look at that code. Here we are back in CBM Program Studio looking at the pulse engine code. I've just declared a bunch of constants here to make it easier to read the code below, giving us an idea of what all the various CIA registers do, the NMI vector locations in lower memory. I have a constant here where I can set the pulse rate. Right now I have it set to 100 Hertz instead of 1 kilohertz. It makes debugging easier. I can see stuff visually change on the screen much better that way. So we have a configuration section here, and for this configuration section we don't want any other interrupts running while we're doing things, so we're turning off interrupts. We're going to save the registers, and we're changing our interrupt vector here to point to our pulse engine. We're setting up the CIA2 timer B to be what we want, and then we have a little testing code here. Just have a counter that counts the number of output pulses we actually output, and I can compare that to the number that were sent to the buffer to get an idea if things went correctly. It makes it easier to see in kind of simulating things. Then we pull the registers back, turn on interrupts again, and we're done. Now the pulse engine itself, this runs as a non-maskable interrupt, so we don't need to turn off the interrupts. Nothing can fire and interrupt this, basically. But we're still going to save the registers, and we're going to clear the interrupt. That way it'll fire next time. And I'm clearing it here at the beginning of the code, so the timer will keep counting from this point, not at the end of the code. So we should have hopefully a little more stable interrupt generated that way. This, wherever you see these 3 asterisks, I do that to tell myself I need to change something. It's a note to myself, or in this case this is testing code. So this is just toggling the top left corner of the screen, and it lets me know that the pulse engine is running. And here's the actual meat of the pulse engine. It is reading from the output buffer. If there was nothing there, it's going to jump down here to the end. If there was something there, it's going to store that data to the port B output. And again, we get into some more testing here. And this is where we're incrementing our counter to know how many pulses we output. And since I needed a 16-bit counter, I did a little increment 16 function as a macro. And I'm toggling another location of the screen, so even if this section of code doesn't output anything sensible, I can still tell that this part's being run by this toggling. This should match this while everything is running. That brings us to kind of a synopsis of the current state of the project. We can generate output bytes from the Commodore code, and we can output those bytes by the pulse engine. And our edge detecting pulse generating circuitry works. The problem with the output generator on the C64 is it only works for 50% of cases when the delta X is greater than delta Y. Now we could take care of that by having a separate loop in there for those cases. What I think might work better and be simpler and take up less code space is to just change the definition of which pins are toggled for the major axis and the following axis. It's also only 2D at this point, although we can add in the Z later. I've marked out a few things here that I've done since I created this slide. I've already tested the output buffer, writing to it while the pulse generator is going, and that works fine. And we already saw that we don't need the set and clear interrupts around the NMI because it can't be interrupted. The big thing is there is no acceleration and deceleration yet. I've actually done this test here already, but we still need to figure out the acceleration and deceleration, and what we mentioned here before about swapping the bits that are associated with the major and minor axis, and then finally wire up some stepper drives and stepper motors and make things move.
Well, I hope you've enjoyed this brief look at the state of the software for the CNC 64 project. It's taken quite a lot of time to get the basics of the buffering system worked out, but I'm really happy where that's at right now. Do a little more work on the Commodore code generation, and then I think we'll be ready to wire that up to some stepper motors and make things move. Then we can get along with making a simple user interface. Shortly, probably by the time the next video is out, I'll have the code up on GitHub so everybody can play along if they want. And if anybody has any questions, just let me know. I've always tried to respond to comments. YouTube doesn't always do a good job of notifying content creators when there's new comments, but I try. Also, if you take a look below, you'll see a subscribe button. Please click on that guy if you haven't already. Once you subscribe, then click on the bell icon, which will let you know anytime I post a video. Sure would appreciate it. Thanks. Until next time.